We're at Point Gratiot here. This is outside of Dunkirk, New York. So this is actually the type section of the Dunkirk Shale, and you can see that kind of exposed along this bank here. The lake's a little bit high, so we don't have as much exposure as we normally do. But it's interesting for a number of reasons that we'll go over here. The Kellwasser event is exposed at this locality there, which is the big Franian-Fomenian extinction event. Again, one of the big 5 mass extinctions in Earth history. There's an erosional lag at the base of the Black Shale that's the result of the internal waves of the pycnocline beveling. That we'll talk about that. And then what I'm standing on right here is actually the glaciated surface of the Dunkirk Shale. So if you look closely through here, you can see these somewhat north-south trending striations along the rock here, and that is in turn overlain by these glacial deposits and tills on top of it here. So basically this sediment up here is about 18,000 years old. This rock here is about 370 million years old or so, something like that. So you're dealing with about a 370 million year unconformity right here. But you don't often see these striations because you can see this cliff kind of comes down and gets washed over here, but every now and then you get some nice exposures of the glacially striated surface. Another feature of the Black Shales here, which we've talked about at length, are the vertical fractures that you find hosted by the Black Shales here. And you can see that here's one of those joint sets running right down through here, but these are catagenic fractures, so these are the result of hydrocarbon generation in the Black Shales, where you have a internal pore pressure that overcomes the confining stress on the rock and cracks the rock and bleeds off that pressure induced by hydrocarbon generation. This is the area of the contact between the underlying Hanover Shale of the Java group and the overlying Dunkirk Shale of the Canada Way group. And there's a lot of interesting things that are going on here right now. So first of all, if we look down here in the Hanover, we can see this is a bioturbated black shale here. So we have a lot of pyrite-filled burrows down in here. We have pyrite-filled burrows in the black shale that you can see running through here. But if you look down here, you can see evidence of this gradational contact, where you have a sharp black shale contact at the base, and then grades into less and less black shale that passes back into the gray shale. So one of the things that we're looking for here is evidence of burn down, which is an oxidizing front when the gray shale comes in over top of anoxic black shales, and the oxidizing front works its way down and it remobilizes trace metals, redox sensitive metals, possibly rare earths and critical minerals and those types of things, and it oxidizes organic matter, and it leaves you with a very sharp contact between the top of that black shale and the gray shale. You don't see that with this bed here. You see that gradational contact with the top still intact. So we're going to sample this bed through here, and we're going to look at the elemental abundances, but we wouldn't expect to see any burn down associated with this bed here. So this is the contact with the Kellwasser bed. Now, this is the bed, the unit that we can trace laterally for tens of miles, and we're going to hang all of our correlations off of. It's actually considered part of the uppermost part of the Hanover Shale, but some publications, some work actually considers it to be part of the Dunkirk. We're not overly concerned with that. We're just using it as a marker that we can show and trace our sections along. But what's neat is you can see these are black shale filled burrows. So these were, you know, burrowed at the time that this gray shale existed there. It was probably somewhat consolidated, and that's why you have a bit of this remnants of what these planolites type burrows look like. And then this is black shale that got piped down into those burrows when the Kellwasser bed was deposited. Now, Kellwasser, that's a German term, and it means kill water. There's two of these. The Pipe Creek is considered the lower Kellwasser bed. This is considered the upper Kellwasser bed. This is the Franian-Fomenian boundary, and this is one of the largest extinction events in Earth's history. So things like stromatoporoids, Devonian reefs were hit really hard during this extinction, and we lost probably somewhere around like 60% of marine life on Earth during this extinction event. And this is the bed that records that. in western New York here. Some dating of some ash beds out in Germany put the age of this at about 372 million years. So that's when this occurred, and there's always this controversy over what caused this. Was it global anoxia? Was it the eruption of volcanics? A meteorite impact? Sort of the common things you hear associated with a lot of extinction event type discussions. Personally, I'm of the opinion that it was probably a combination of things. If you look through Earth history, there's impacts that, like the one that ended the dinosaurs, there's the eruptions of basalts like on the same scale at the end Permian, or even the Deacon traps at the end of the dinosaurs, that life makes it through just absolutely fine. You see no evidence in the fossil record of extinction, unless they're like some unlucky fish that happen to live right where the meteor hit, in which case you're screwed. But you see things that are blamed as the sole cause of extinctions, that life makes it through in under situations, which leads me to believe oftentimes if you have a lot of controversy about 3 probable causes or 2 for an extinction, it was likely a combination of all those stressing the system to the point of breaking, which could very well be what's going on here. With this precise age date of this bed, we really don't have any eruptions or impacts that precisely coincide with that we can consider a smoking gun, which brings things like global anoxia, you know, and drowning reefs and anoxic waters and things like that is playing a large role. But again, that's not to say that some of these other processes didn't stress communities to where it didn't take much to break them. So this project, one of the things that we're looking for are thin black shale beds that occur interlayered with gray shales. And the hope is that we can find evidence where processes, diagenetic processes such as burn down, might have concentrated elements and minerals of interest within those black shales. And the most likely spot for that to happen is what's represented here by just a few centimeters of gray shale between the Kellwasser bed and the Dunkirk Shale here. So as we start tracking this to the east, this section is going to expand to probably somewhere in the neighborhood of like 7 or 8 meters in thickness here. So we're at the most distal edge of this section that we can find in the Appalachian Basin, at least in western New York State. So that's where we're starting this whole story, is we want to characterize what's going on here at Point Gratiot with this very narrow, thin gray shale. And then we're going to see where this thing expands as we start tracking these beds to the east here. And the last thing to say about it is the thinness of this section here is due to a number of processes. So we have condensation, we have sediment starvation because of our distal setting in the basin, but with that you're also ripe for erosion, internal waves and those types of things. So we also do see a lot of this interval is being chopped out by erosional overstep, and we'll find some examples of it. But here at the base of the Dunkirk we can find a pyritic lag and that's in there, and what that's the result of is this erosion of this underlying gray material. Anything that's carbonate gets dissolved, anything that's light clay, silica material gets winnowed away, and you're left with this pyritic lag that's created of all this pyritic material that we're seeing here in this gray shale. So this is all the types of these worm burrows and things like that that accumulate in these pyrite lags. What we're going to do now is we're going to measure this section out so that we understand the exact thicknesses of the beds here, and then can tie that back into the sample catalog that we're going to take through this section up through here and into the base of the Dunkirk. So that's what we're going to do now. We got better spot. That's 5 inches of pyritic gray shale. And then 1 inch of black shale. And then we have about half an inch of gray shale. And then half an inch of interbedded black and gray shale. Might need you to pump that.
Yeah.
That's good. Scott McCallum, right there.
Am I supposed to introduce myself now?
Yes, introduce yourself. Scott McCallum, geologist, petrophysicist, statistician, and data analyst, even though he doesn't like to be called that. He's one of the best. So we have all these spots you can see here where we have collected a whole bunch of samples very close together. So you want to tell us what the heck we're doing here?
Yeah, I'd asked Randy if when we collect at least this first location, if we could collect the samples from every specific sub-location, like this being a sub-location, collect samples in triplicate, so we can see if there's any variation within a bed that we think everything should be the same. And then for each one of these samples that we collect, we'll also measure in triplicate just to understand the variation that's in the measurement. So we have variation at a sub-location, so a location specific to where we are, and also variation within the measurement. If we determine that all of this is pretty minimal, then we don't necessarily have to do quite as much sampling at some of the other locations. But initially we wanted to start out collecting, possibly oversampling a bit, just to understand the variance in the measurement and at the location as well.
So one thing we want to make sure we do here is recognize the people and the groups that are supporting this work. This wouldn't be possible without Mike Bingle Davis with Energy Minerals Division of AAPG, really working hard to try and get us some sponsorship and get our name and our work out there to people that might be able to fund this type of research. Justin Birdwell at the United States Geological Survey is going to be providing a lot of analytical work on these samples. So we're greatly indebted to them. Millie Wright with Chemostrat is also working hand in hand in this project to provide analytical work and the XRF data and some of the ICP data that we will be collecting on this. So again, thank you very much to those groups for helping us out with this research. All right, so we are now about 3.5 miles east of Point Gratiot, where we were previously working there. And so we're starting to move in the direction where this unit between the Kellwasser bed and the Dunkirk is beginning to thicken and splay out into more of these interbedded black and gray shale intervals. So I'm standing right here in the Hanover Shale, and right here is the Kellwasser bed on this creek. So we can find it right here. So this is our datum. And then you can see when you move up here, and there's a little bit of sloughing, but you can see this gray shale interval is actually much thicker. And here's one of these first black shale beds that are coming in. And then we have an erosional surface here. So this is actually a black shale full of pyrite that's in over top of it before getting up into these gray shales. And then we're into the overlying Dunkirk Shale formation up through here. So that's what we're starting to deal with. Again, it's still a relatively condensed section here. We haven't moved that far away, but we're starting to see these other units come in. Now, this is a really weathered, chippy section. We actually did all of our sampling up there, you can see, but that waterfall is incredibly loud, and I don't think you'll be able to hear me. So that's why we're looking at this section here. But that's the deal, and that, I think we're about done for the day now. So it's about 4:30. We've been at this for quite a while. So anyways, thanks for joining us, and we'll see you on the next time.